In this video, I want to talk about how transcription ends, or how transcription terminates in prokaryotes specifically. So there are two ways. There is row-independent termination, which is also called intrinsic termination. And there's row-dependent termination. Row is a protein, we'll talk about it shortly. But in the case of row-independent termination, the row protein is not used. Instead, what happens is a hairpin loop forms due to these things called inverted repeats in the DNA, and that signals the end of transcription. So if we imagine this being our DNA strand and RNA polymerase is going along transcribing RNA, eventually this thing, the mRNA itself, loops around itself. This thing is the hairpin loop. Once that hairpin loop forms, that signals to the RNA polymerase to stop transcribing, and then the RNA polymerase falls off. Now this RNA polymerase is in a prokaryote, right? So it must be the core enzyme. So how does this hairpin loop actually form? That's something we'll get to in just a moment after we talk about an overview of row-dependent termination. So if it's row-dependent termination, the row protein is used. So what happens? The row protein, keep in mind this little symbol is the Greek symbol for row. Row travels along the RNA transcript until it reaches RNA polymerase. And then it causes the RNA polymerase to dissociate from the DNA. Okay, so if we imagine this to be our DNA strands, this is RNA polymerase, it's going through making RNA, then this little row protein hops along. Now row is going to travel along this mRNA until it reaches RNA polymerase, and when it does, it's going to cause the RNA polymerase to fall off, dissociate, and of course the row protein itself will fall off. So that is how row-dependent termination works. That's pretty much it. Now let's talk a little bit more about row-independent termination, how this hairpin loop forms. We said that it forms due to these things called inverted repeats in DNA. So here are details on the inverted repeats. So if this DNA strand is running 5' to 3' this way, and 5' to 3' this way for the bottom strand, let's imagine this top strand being the template strand. So this here, this green portion or these green portions rather, are the portions in which we have these things called inverted repeats. So this is an inverted repeat here, inverted repeat, repeat. And over here, this is also an inverted repeat. I'll just put inverted repeat IR here. Okay? Why is that? What does that even mean? Well, notice that here we have G, 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 C, 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 G, C, G. Now, if we start off from here to here, right? Or actually, here we had 9 bases, right? 3 G's, 3 C's, and then a G, C, G. Over here, we also have 9, and it just so happens that if you start here, it's going to be complementary to these. So here, we ended up with a G. Here, we're starting with a C. So the C is complementary to this G. So if you read this one going this direction, you will find that it's complementary to these going in this direction. So here we have a C is complementary to the G, a G that's complementary to the C, the C complementary to this G, these 3 G's complementary to these 3 C's, and these 3 C's complementary to these 3 G's. So what happens when this template strand is transcribed into RNA? Well, this is what we get. we get this RNA strand. Okay, this strand here is the RNA, and it has these inverted repeats that are bound by the red lines here and written in green. So what happens here is that the strand sort of bends on itself. This side comes in this way, and this side kind of bends in this way, and then we have the loop formation. And why is that? Well, because now this C, see if I can get a good color here. If I can get this C, it's going to hydrogen bond with this G. This G is going to hydrogen bond with this C. And this C will hydrogen bond with this G. And the rest of them are complementary, so they're all going to hydrogen bond. So we're going to have hydrogen bonds here, 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 and here. And that's going to hold and this hairpin loop together. And typically something to note about this is that usually these are very GC-rich regions. Why would that make sense? Well, GC base pairs have 3 hydrogen bonds. AU base pairs have 2 hydrogen bonds. So if we want to make sure that this hairpin loop stays together, it would make sense that the GC base pairs kind of make up at least most of it. Here I've drawn it all. It's not necessarily going to be the case. I just wanted to emphasize the point or exaggerate the point. But there could be AU base pairs in here. So that's how this hairpin loop forms. And once this hairpin loop forms, it signals to the RNA polymerase, hey, stop polymerizing. We're done here. Okay? And those are the ways that termination can occur in prokaryotes. Now, what about termination of transcription in eukaryotes? It's a good question, and the reason why it's a good question is because this idea is not really totally understood yet. It's not really well understood how termination of transcription occurs in eukaryotes. So I'm not going to make a video about it simply because I don't know, and scientists don't really know too well. So I hope that video was helpful overall, but not disappointing at this little point here. That's about it. One last thing, I am a tutor. If you live in Southern California, feel free to contact me via email at moofuniversity@gmail.com and see the description for more details. Thank you for watching.